So hi guys, we are once again back with another video. That is, we're going to discuss the structured essay of the paper 10, right? So if you have not yet covered the MCQ discussions, you will have to cover that first, and then thereafter you can come to the discussion of structured essay, right? So in this video, we are going to discuss two structures. So one from mechanics and then another from thermal physics, right? And then also we have two problems, right? So one from once again mechanics and the other from waves and oscillation, two essays, right? So one from Doppler effect as well, right? So yeah, let us get back with the discussion. All right. So yes, initially it says uniform circular disk of mass m and radius r, okay, mass m is mounted on a horizontal or mounted horizontally on the smooth table as that if it is free to rotate about a frictionless vertical axle. This is free to rotate around a frictionless vertical axle, right? A light string which is tightly wrapped few times. So this string is tightly wrapped few times around this disk, right? And then they are saying of the disk passes over a pulley P. So this string passes over pulley P and carries a weight B, of mass simple M, right? Of mass simple M uh, at the free end as shown in the figure. The moment of inertia of the disk about the axis of rotation is this. They have given the moment of inertia as well, right? The moment of inertia of the disk around this axis. The system is held at rest. Okay, it is held at rest with string taut and released at time t equals 0. Released at time t equals 0. What type of motion will A and B have? Okay, so this is A. What kind of a motion would A have? What do you think? What do you think it's going to be? So you can see, right? So A is a circular disk, which means, and then this is a mass, right? So when this mass moves down, vertically down, this is going to rotate, right? This is going to rotate. That is what's going to happen. So A is going to perform a simply a rotational motion, right? A rotational motion. And what kind of a motion will B perform? B is going to vertically go down, which means it's going to perform a linear motion, right? Linear motion. Okay, fine. Next, they are asking uh, if the angular acceleration of A is alpha, if the angular acceleration of A is alpha, if this is rotating with an angular acceleration A alpha, and the acceleration of B is A, and the acceleration of B is A, write down a relationship between A and alpha. Now you see, if this object is moving downwards with A acceleration, so along with this object, this string is also vertically moving downwards with A acceleration, which means this part of the string will also move horizontally with A acceleration, right? So, if you consider the wheel, right? If you consider the wheel, in this manner, right? The top view of the wheel, this is the radius R, right? So this kind of an acceleration is there to the wheel, a linear acceleration, right? So it's rotating with alpha. So how do we relate this? Actually, this is the tangential acceleration. How do we write the tangential acceleration? AT is equal to R alpha. So here, the AT, the tangential acceleration is simple A is equal to R alpha, right? So that would be the answer, right? Then thereafter, they are asking what is the relationship between the torque acting on the disk and alpha. If the torque acting on the disk, if we assume it to be as tau, right? If the torque acting on the disk, if we assume it to be as tau, we know tau is equal to what? We know tau is equal to I alpha, right? So corresponding F equals ma motion, F equals ma for linear motions, So tau equals I alpha for circular motions, right? So that is how we use this equation. So in that case, tau equals I alpha. So actually they have given I to be as what? They have given I to be as half m r squared. So therefore I replaced as half I m r squared into alpha, right? Fine. Then they are asking, after a short time, if the string suddenly breaks, what will happen to the motion of A and B? Let us assume the string breaks from this point. So, which means now this object is not going to have any upward tension. It's not going to have any upward tension. It is only going to have its weight acting downwards. So therefore, it will move down with an acceleration g, right? It's going to perform a gravitational acceleration, right? So B is going to perform a simply it's going to perform a motion under gravity, right? So motion B is going to perform a motion under gravity, right? Okay. What about A now? So A initially the object A had a tension due to the rope. It had a tension T, right? Now when the string disconnects, this tension is not going to be there anymore, right? This tension is not going to be there anymore, which means what? Now the object doesn't have a tension. Actually, it doesn't have a tension, which means it doesn't have a torque, which means it doesn't have a angular acceleration, right? It doesn't have angular acceleration. If it doesn't have a torque, it doesn't have an angular acceleration as well, right? So you can see if the torque is zero, angular acceleration is also going to be zero, right? So simply in that case, the circular disc is going to perform a motion with a uniform angular velocity, right? It's going to perform a motion. It's going to rotate with a uniform angular velocity, right? It's going to rotate with uniform angular velocity, right? Okay, fine. Now what? And in the D part, they say after the string has broken, as mentioned in C, a second disk of the same radius, but like after the string has broken, as mentioned in C, a second disk of the same radius, but same radius, right? Another disk of same radius, but different mass, M over 2, which is at rest is dropped, which was initially at rest, was dropped symmetrically on disk A. The two disks were found to stick together and rotate. What principle would you use to determine the new angular velocity of the disks? It's like this. Initially, uh, while the while the this thing was rotating, another disk of the same radius but different mass. This was mass M was dropped on this, right? This was dropped on this. Initially, this was at rest, right? This was at rest, right? So after dropping, both join together and rotates together, right? Now the total mass is 3m over 2. So in this kind of situation, what kind of principle would you use to determine the new angular velocity of the disk? Let's assume this is rotating with a new angle omega dash, right? So initially this was rotating with a certain omega naught maybe, and if you assume it was initially rotating with omega naught angular velocity. The disk was initially rotating with omega naught angular velocity, let's assume. And then another circular disk was dropped on this. So once the mass of the system changes, the inertia of the system changes. As a result, the angular velocity of the system would change as well, right? So what principle would you use to determine the new angular velocity? Simply it's the conservation of angular momentum, right? We are going to use what? Conservation of angular velocity, right? Conservation of angular velocity, right? Under what condition is the above principle valid? Under what condition is this above principle valid? So in order to use this conservation of angular, so not angular velocity, right? Angular momentum, right? It should be angular momentum. So in order to use this conservation of angular momentum principle, what is the condition that it should satisfy? It should satisfy a condition called there should not be any external torque acting on the system, right? There should not be any external torque. No external torque. No external torque acting on the system. If and only if this condition is true, you can apply conservation of angular momentum, right? So the third part is if the angular velocity of the disk A, okay, this is the disk A, right? This is the disk A. If the angular velocity of the disk A prior to dropping the second disk is omega naught, right? Okay, what we have assumed was true, right? Okay, omega naught. If it was rotating with omega naught, find the new angular velocity in terms of omega naught, right? So this was initially 0. It had 0 momentum. This is initially it's going to rotate with omega naught. So yeah, so to solve this, we can use, so simply let us assume the initial I value of this is I. The new I is I. Now let's assume the I of this is I naught, right? I naught. I mean, I means what? The moment of inertia, right? The moment of inertia. So what we are going to use here, conservation of angular momentum. Initial angular momentum is equal to final angular momentum, right? So what is the initial angular momentum of the system? Initially, this was rotating with 0 angular velocity. So simply I naught into 0 plus this disk was rotating with omega naught. So I into omega naught is equal to, now finally both these are rotating together, which means the moment of inertia is I plus I naught, isn't it? I plus I naught is rotating with, let's assume, omega dash. So omega dash will be I omega naught, I plus I naught. So what is I? I they have given to be as mr squared over 2 omega naught. I is mr squared over 2. So I naught is what? Mass is m over 2. Mass is m over 2. They have told the mass of this guy is m over 2. So when we find the moment of inertia of that, we need to substitute m over 2 to this mass position. Instead of the mass capital M, it's going to have a mass of m over 2, right? So in that case, we're going to put m over 2 there. R squared over 2. So if you simplify this, you're going to get 2 over 3 omega naught, right? We're going to get 2 over 3 omega naught, right? Okay, so let's discuss the E part. In the E part, it says, instead of the string breaking, as mentioned in C, suppose the axle breaks and the disk becomes free to move. So what they're saying is, instead of this string breaking, what if the axle breaks? What if the axle breaks and this becomes free to move? Now this breaks. No, sorry, not this doesn't break, right? Now of course what happens is this doesn't break. What breaks is the axle. Axle breaks. What happens? So when the axle breaks, so now this is not fixed. The the circular disk will not be fixed in that case. While this was rotating, initially it was rotating, right? While rotating, this will move forward. While rotating, this will move forward, right? So what type of motion will A have? So while rotating, A will move linearly forward, right? A will move horizontally while rotating. A will move horizontally while rotating, right? Rotating. Will the angular acceleration of A remain the same as in B? What would the answer for that be? Will the angular acceleration of A remain the same as in B1? B1 means, will the angular acceleration of A be the same? Will, like, after the axle breaks, this is going to move forward, right? This is going to move forward, right? So when it is moving forward, what they're asking is, will it once again move forward with the same acceleration? No, that's not going to happen. Why? Because the tension will change once this axle breaks, right? So the tension will change actually, right? So therefore, the answer will be no. Why? Because the tension of the string changes. Therefore, alpha changes. Therefore alpha changes. That's enough. Therefore, alpha changes, right? So yes, the first structured question we have discussed, right? I hope you got a clear idea of it. So let us move on to the next, guys. We have discussed the first structured question properly, but still, actually, we're not going to discuss the second structure in this video. That is, the main reason is we have not yet covered the experiment in our thermal class for 22 students. We have not yet covered the experiment cooling, the method of cooling, right? So we have not yet covered this experiment. So therefore, actually, we're going to cover it very soon, right? So maybe this week, right? So therefore, after covering the experiment, I will add the discussion of this structure separately into the same playlist, right? So and then I will update it in the group, right? So therefore, for the time being, let us discuss skip the second structured question, right? So and then we will move on to the essay discussion, right? Let's move on to the essay discussion, right? So here, the first essay discussion that we have is going to be based on simply the mechanics, hydrostatics part, right? So yes, let's read the problem first. It says an empty boat floats in water with 10% of its volume submerged. Okay, initially an empty boat, right? Submerged in water. And when it is loaded with 1200 kilograms, the volume submerged will increase to 70% of the total volume. The first question is, calculate the mass of the empty boat. We need to calculate the mass of the empty boat, right? Let us do a small workout for this, right? So actually, all right. So if this is the part B, first problem, right? So there is a boat, right? Initially only 10% of its total volume. 10% of its total volume is, if the total volume is V, 10% of its total volume is submerged in water, right? So let us assume its mass to be as, So yes, let us assume its mass to be as the mass of the empty boat. Let us assume it to be as mg, right? So in that case, if it is floating, then an upward force from the liquid is going to act on the boat, that is the upthrust force, right? So let us write an equation for this. Since it is floating, the weight should be equal to the upthrust. The weight mg will be equal to what is the volume that is being what is the dipped volume? It is 10% of the total volume. What is the let's assume the density of the liquid is rho g, right? So actually this cancels. M is equal to 10v over 100 rho. This is the first equation, right? And then they are saying once again, when a certain mass of what is the mass exactly? When a mass of 1200 kilograms, right? So when a mass of around 1200 kilograms, right? When a mass of 1200 Newton is inserted into the boat is going to dip to a volume 70% of its volume. It's going to dip 70% of its total volume, right? So it's going to dip 70% of its total volume, right? So in that case, the mass, the weight of the boat is always going to be there, right? So let us mark it as always. The weight of the boat is always acting downwards, mg. And then now, of course, a new upthrust force will act, u dash, right? A new upthrust force will act. Now, if we write the equation, it is going to be mg plus 1200 into g is equal to u dash, right? So m plus 1200 g, what is the new dipped volume? 70 v over 100 rho g to g cancels, right? M plus 1200 is equal to 70 v over 100 rho, right? This is the second equation. So if we need to find capital M, what we could do is we could simply divide the second equation by the first equation, right? So we can divide the second equation from the first equation, M plus 1200 over capital M, 70V rho over 100 divide by 10V rho over 100. Rho to rho cancels, 100 to 100 cancels, 10 to 10 cancels, V to V cancels, right? So 1 plus 1200 capital M is going to be 7, right? So 1200 over M is equal to 6, right? 6, which means M is going to be equal to 200 kilograms, isn't it? M is going to be equal to 200 kilograms, right? So yes, that is done, right? So we have found the mass of the boat, right? So let's go for the next question. All right, so the second problem is, if a leak develops and water starts to enter the boat, which is loaded with 1200 kilograms at a constant rate, right? So if a leak develops and water starts to enter the boat, which is loaded with 100 kilograms at a constant rate of 100 kilograms per minute, for how long the boat can float before sinking, right? So they're saying simply, if by chance, if a small hole develops in the boat, right? If a small amount of hole, a small hole develops in the boat, right? So initially, how much is it dipped? 70V over 100 is dipped. What is the undipped volume? What is there yet to be sunk? 30 over the 30% of the volume is still possible to sink, right? So when water comes in, right? When water comes in, what happens? The water will fill up. What is the amount of volume that the water has to fill up? It has 30% of the volume of the boat to fill into, right? So therefore, let us assume the mass of water that comes in, right? The mass of water that comes in, the mass of water that comes in is, let's assume M, right? M. So what will be the volume of it? It has 30 VO 100 amount of volume to fill into, right? So what is the mass of the density of the liquid? Rho. So this is the third equation. Actually, this amount of this amount of mass of water can further come in, right? Because that amount of when that amount of mass of water comes in, this completely fills this volume, right? So we already know one equation. What is it? Capital M is equal to the 10 V over 100 of capital M is. So the first equation I can write once again as how. So it is 200, right? 200 kilograms is equal to 10% V 100 rho, right? So the first equation I modified, right? So 3 divided by 1 dash is how much? So M over 200 30V rho over 100 divided by 10V rho over 100. This to this cancels, this to this cancels, V rho. So mass is equal to 600 kilograms, right? So 600 kilograms of water can yet come inside inside the boat so that it completely submerges, right? So to fill 600 kilograms, what amount of time would it take? The saying 100, it fills per minute 100 kilograms, right? Per minute 100 kilograms is filled, right? The saying M over T is 100 kilograms per minute, right? So to fill 600 kilograms, therefore the time taken will be what? 600 kilograms divided by 100 kilograms per minute. If you see, it's going to be 6 minutes. So 6 minutes will be taken in order to completely submerge the boat, right? So this is how we're going to do this problem by the second question. All right. So okay, guys. So let us go for the next question. That is the third one, right? So let's see. What is the minimum force? What is the minimum force required to shift the sunk boat, to lift the sunk boat without the load, right? To lift the sunk boat without the boat up to the surface of water. They have given the average density of the material to be as 1500 and density of water to be as this much. So this is quite a tricky question, guys, right? So it's not quite easy as you think, right? When compared with the above two questions, this is not going to be pretty easy, right? You need to think in deep in order to solve this, right? So it's just 1 or 2 lines of simplification, but the concept is, there's a deep idea, right? So therefore, like, give 100% priority for this question. I think this is the most important question out of the complete question, right? So in each essay question, there will be one important sub question that you need to analyze in detail, so that it would the concept that you understand out of this question would be useful in your future problem solving things, right? Okay, fine. Let us see. I'll mark it, right? So yes, fine. Let's move on. So this is the third thing, right? Third question, I guess. All right. So it says, right. Okay, the third one. They're saying, so this is the surface of water, let's assume, right? So let us assume this is the surface of water. Now the boat is kind of sunk somewhere here. Like let's assume this is the boat, right? Now, so this is water. All right. First of all, try to draw a proper figure. Then it will be easy for you to understand stuff, right? Okay. Now, in order to lift this, so first of all, let us see what are the forces acting. The forces acting is the weight of the boat, that is 2000 Newton, 200 kilograms. So therefore, it's 2000 Newton, right? And then what? And then the upthrust acting on the boat. Upthrust acting on the boat, UB. Now you need to understand in this case, right? So like you do not have to consider the mass of this thing water which is inside the boat. You do not have to consider the mass of water which is inside the boat, right? Because when you for example, now if you dip, for example, if you kind of just give me a second. Yeah, so like assume now if you dip a bucket inside a well, right? So when the bucket is inside the water, right? If this is the water surface, when the bucket is inside the water surface, it's not quite difficult for us to lift it, right? It's not quite difficult for us to lift it. But when you lift it above the water surface, it's not only the mass of the bucket, also the mass of water which is inside the bucket will come into play, right? But when the bucket is inside water, only the weight of the bucket will be acting downwards, right? Because the medium is completely water, the weight of the water inside this will separately not act on the bucket in the downward direction, right? So the same concept is here as well, right? So when the boat is inside water, right, the water column which is inside the boat will not create a downward weight. You need to be very clear on that, right? Because most of you guys might not understand that concept, right? So therefore, the water column inside the boat will not create a downward weight. All right. Okay. Fine. So, right. So now we need to supply an upward force. What is the minimum force required? What is the minimum force required to shift it upwards? All right. So minimum force means when it just starts to move up. When it just starts to move up, the upward force is equal to the upward forces F plus U is equal to the weight, right? So the upward force F is equal to mg minus UB, right? After setting of the boat. So what is the weight actually? 2000 newtons, the weight of the boat. So what is the upthrust acting on the boat? The upthrust acting on the boat is due to, now this is, you need to be very clear, the upthrust is acting only on this volume. It's acting only on this volume, not this complete volume, You need to be very clear on that, right? So it's not acting on this complete volume. Instead, it's acting on this piece of volume, right? Because this is water medium exposed to the environment, right? So yeah, so this is the medium. It's like a flat rod, right? So when a flat rod is inside water, are we going to consider the water column above the flat rod when we apply upthrust flow, right? We consider only the volume of this rod. So similarly, the only difference is in this case, it's kind of a bent, right? So yeah, pretty much, I guess you got the idea, right? Okay, fine. Let us move on. In that case, fine. Now what? What is the upthrust? Upthrust is the volume of this boat. The volume of this boat can be found how? The volume of this boat can be found mass of the boat divided by the density of the boat. The density of the boat. This is going to give the volume of the boat, right? Volume of this region, right? Volume of this region. All right. So this is the dipped volume. Dipped volume, right? That's the dipped volume. What is the density of liquid? 1000. What is the G? 10, right? V rho G. So this is actually V rho G. V rho G. What is the V? V is this dipped volume. How did we find it? By dividing the mass from its density, mass of the boat from its density, right? Okay, so if you simplify this, you're going to get something around 1750 newtons, right? So this would be the minimum force required to lift the boat to the surface. But beyond the water surface, if you're going to lift it, then the uh, mass of water which is inside the boat will also act downwards, right? So hope you understood that, right? All right. So let us go for the fourth question. It says the mended boat with another load of 200 kilograms. The mended boat with another load of 200 kilograms on board while sailing suddenly enters a region where water is uniformly mixed with tiny air bubbles, right? So the boat enters a region where water is uniformly mixed with tiny air bubbles. If the average volume of an air bubble is 1 cubic millimeters, right? And the air bubble concentration is 3.5 into 10 to the power 8 per cubic meter. In 1 cubic meter, this much of air bubbles are there. That's what this concentration means, right? And then they are saying find the effective density of water. Let's find the effective density of water first, right? So let us plot a small diagram for this, right? So this is the fourth question, right? So it's like this. So initially, there is a, maybe that's the boat, right? That's the boat, and inside the boat there's 200 kilograms weight or something, but that's not what it matters initially. Inside, so when you consider, if you consider 1 cubic centimeter, there's air bubbles. There's a lot of air bubbles in this water, right? So there's a lot of air bubbles. So likewise, there's going to be plenty of air bubbles, right? So now, what they're asking is the effective density. So if you see, if you consider 1 cubic meters, 1 cubic meters, they're saying there are 3.5 into 10 to the power 8 bubbles. This much of bubbles are there. 3.5 into 10 to the power 8 bubbles are there, right? And then also they are saying the volume of one bubble is what? It is 1 into 10 to the power minus 9 cubic meters, like 10 to the power, like 1 cubic millimeter means, actually they have given it in cubic millimeters, right? So we have converted it into cubic meters. That's the only difference, right? So yes. So then I need to find the total volume of the air bubbles inside 1 cubic millimeters, right? Next I'm going to find what? Total volume of air bubbles in 1 cubic meter. Total so one air bubble is this much. How many air bubbles are there in 1 cubic meters? This much. So simply we need to multiply, right? 3.5 into 10 to the power 8 into 1 into 10 to the power minus 9. In that case, you're going to get 0.35 cubic meters. You're going to get the total volume of air bubbles as what? This much. So if you consider 1 cubic meters, right? It's like this. If you consider 1 cubic meters of water, right? Inside this, there's air bubbles, right? If you consider 1 cubic meter of water, inside this, how much total volume of air bubble? 0.35 cubic meters. So then what is the actual effective remaining area of water? Actually, water is there how much? The volume of water there. It is 1 minus 0.35, which is 0.65 cubic meters. This much of water is there in what in the 1 cubic meter of water. So this much of actual effective water is there. So if you consider 1 cubic meter of water, what is the mass of 1 cubic meter of water? 1 kilogram, right? Isn't it? Like it's 1 kilogram. 1 cubic meter contains, 1 cubic meter contains 1000 kilograms. Right? According to the definition, right? 1 cubic meter contains 1000 kilograms, right? Because the density of water is 1000 kilograms per cubic meter. In 1 cubic meter of water, there is 1000 kilograms of mass of water, right? But actually now, what is the volume of this, right? So we know that in in 1 cubic centimeters, there's 1000 kilograms of water. So, but how much actual volume of water is there? What is the actual volume of water present after the presence of water bubbles? Actually, there's 0.65 cubic centimeters of water. In that, we need to find how much this thing. So it's going to be 0.65 multiplied. This amount of water mass is going to be there. Right, this amount of water mass is going to be there in 0.65 kilograms, 0.65 cubic meters. So we need to find the density now. The density is equal to mass divided by volume. So in this 1 cubic centimeter of volume, what is the what's the mass of water? This much, 1000 into 0.65 kilograms, right? So if you simplify, you're going to get 650 kilograms per cubic meters, right? So if you understood, that is going to be the effective. We need to next check whether, like, we have found the effective density of water. We need to check whether the boat would sink or not, right? So yeah, we need to show that the boat sinks. Right, now we know that the boat is now under which kind of a thing, like, okay, this effective density of the liquid is going to be what? The effective density of the liquid is going to be rho is equal to 650 kilograms per meter cube. In that case, the upthrust acting on the boat will change. New upthrust, right? U dash new, it's going to change, right? So what is the downward forces initially? If we see, there's going to be there's a 200 kilogram weight, which means 2000 Newton from there, and then like also the weight of the boat is there, which is once again another 2000 Newton, which is all together. The downward force is what? Altogether the downward force is 4000 Newtons, right? That is the downward force, right? So we need to find the upthrust force, U dash nu, right? If we see that, it's going to be what? V rho G, V rho G, right? It's going to be V rho. Yeah, so let us find the U dash nu, right? So in that case, the U dash nu is going to be, right? What is the volume? 2 cubic meters. The volume of the boat is 2 cubic meters. Rho is now 650 kilograms per cubic meter, and 10 meters per square second. In that case, it's going to be 1,300 Newton. 1,300 Newton. Now this upthrust force is less than the downward force, that is 4,000 or something, right? 4,000 Newton. If we see with like with both the mass of the boat and the weight on it, somehow it's less than 1,300, is less than this, which means the upward force is less, which means therefore it will sink, right? Therefore it will sink, right? So how did we get this 2 cubic meters? The volume 2 cubic meters. This was found using the initial concept, right? That is somewhere here. We got to know that the mass of the boat was 200, right? So if we use this equation to find the total volume of, if like the total volume of the boat, is assumed as V, right? So we have an equation this. So if we substitute, like, the mass of the boat is 200, right? So rho at that moment was 1000. So if we substitute this, we will get V to be as 2 cubic meters. This is the total volume of the boat, and this is the total volume of the boat. So therefore only we took here the volume of the boat to be as 2 cubic meters, because like, even if it completely dips, right, like it's like this. If it completely dips in this way, this kind of a way, right? So still it will not float. It will not float. In this case, then only like we consider the upthrust new, right? Upthrust new. So the total volume is sunk in this case, right? The total volume is sunk, but still the upthrust will not be sufficient enough to balance the downward forces, right? It's not going to be sufficient enough to balance the downward forces, which means it will definitely sink, right? For the boat will sink. Hope you understood that, right? Right. So then they're saying, use the effect described in 4 to explain the dangerous act. Okay, the danger in the following act. What is that? There is a deep pool at the foot of a waterfall. A person starts swimming closer to the foot of the fall, right? So actually, it's quite dangerous for us to swim closer to a foot of the waterfall, right? So when water falls, right? If we assume this kind of a pool, right? In a waterfall, the effective density of water decreases. Why? Due to air bubbles, due to formation of air bubbles, the effective density of water decreases. When it decreases, what happens? So like if this is the man, right? If the effective density decreases, his weight is acting downwards, mg. The upthrust acting on him is u, v, rho, g. The only upward force that prevents the swimmer from sinking is this upthrust force. So somehow, if this upthrust force is somewhat higher, then he can float, right? So the effort that he needs to put to float is somewhat less in that case, right? So what has happened is, due to the effective density decreasing, this density decreases, which means the upthrust ultimately decreases, right? When the upthrust decreases, so the chances of the swimmer to sink is somewhat high, right? When the effective density decreases, the upthrust acting on him decreases. Therefore, the chances of the swimmer to sink is high, right? So this would be the explanation. You will have to write it on your own words. All right. Okay. All right. So let us move on to the second problem, guys, right? So this is a question related with waves and oscillation, right? And also more importantly, this is a question related with the Doppler effect section, right? So let us see. What they're saying is, explain what is meant by Doppler effect. And then they are asking a few applications of Doppler effect, right? They're asking few applications of Doppler effect. So simply, Doppler effect means what? So Doppler effect means the change of an apparent frequency, the change of an apparent frequency of a sound due to relative motion between the source and the observer, right? So simply it's the change in frequency due to the relative motion between the sound and the source and the observer, right? So and also if you see some applications, the applications are so Doppler effect is used to determine the speed of moving vehicles. Like you might have seen police officers, in like traffic officers, they use speed guns to determine the speed of moving objects, moving vehicles, right? So here the principle used is simply the Doppler effect to find the speed of body cells. This is also in medical industry also Doppler effect is used, right? So to determine the speed of celestial objects, right? So like we need to actually determine the speed of motion of celestial objects as well. So we use the light rays coming from them, and we see actually what we are using in that case is also Doppler effect, right? So okay, and then they are asking us to simply demonstrate the Doppler effect using ripple tanks, it seems, right? So how do we use ripple tanks to how do we use ripple tank to uh, do this experiment? Like I mean, to demonstrate the to demonstrate this thing. Simply what we So this is how, guys, this is how the demonstration in a ripple tank is done, right? So that the Doppler, right? So what you have to do is you have to move the pointer, right? So while you are vibrating it up and down, right? While you're vibrating it up and down, you'll have to, while you're this thing vibrating it up and down, you'll have to move the ripple tank, right? So the vibrator. In that case, an observer would observe the ripples as this, right? So the observer would observe the ripples as this, like actually it's going. This is how the wave fronts are going to look like. So this is the normal wave fronts, right? When you vibrate the when you vibrate the vibrator at the same point, right? So this is how the wave fronts are going to look like. But when you are moving the vibrator while vibrating, this is how it's going to look like, right? So this is how the demonstration is done, right? So if you see this kind of a wave front, that means it's corresponding to a Doppler effect. All right, so let us move on to the next problem, right? So it says a boat is traveling with 18 kilometers per hour towards a small cliff, right? So and then it sounds its horn at a frequency of 335 hertz. This is the actual frequency of the horn, right? So now this is the boat is the source. The source is the one who is moving towards the cliff, right? So the speed of sound also they have given it to be as 340 meters per second. So what they're asking is find the frequency of the horn as heard by a boy on the cliff, right? So if we consider there's a boy on the cliff, right? So this is the boat, right? So like if we assume, okay, this is the boat, right? And so the sound produced by boat is moving in this way with a velocity what? Velocity v 340 meters per second. That is the speed of sound, right? So with what frequency? 335, right? It was 335. Yeah, 335. So in that case, it's going to be 335 hertz. The vehicle is moving with 18 kilometers per hour, which means in meters per second, it's moving with 5 meters per second, right? So the boy is on the cliff, the observer is on the cliff, right? Observer is here, the source is moving towards the observer, right? So this is the source, guys, and the observer, right? So we know the equation for the apparent frequency, right? So we need to find the apparent frequency. In order to find the apparent frequency, we know the equation, that is the velocity of sound, initially velocity of sound relative to the observer, right? Divided by velocity of sound relative to source, right, into the original frequency. So the apparent frequency, if that is heard by the person who is on the cliff, is so what is the velocity of sound? What is the velocity of sound relative to the observer? The observer is at rest. So the sound, the velocity of sound will be simply 340 itself, right? It will be 340 itself, right? So what is the velocity of sound relative to the source? Now, the source is also moving forward. The sound velocity is also moving forward. Both the guys are moving in the same direction. So what is the relative velocity between them? So if you need to find the relative velocity between two two objects, I mean like two different parties, which is moving in the same direction, in that case, we're going to get what? 340 minus 4. Like we need to subtract, right? So we need to subtract 340 minus 5, right? So this is it uh, into the original frequency 335 hertz, right? So in that case, if we get the value, it's going to be something closer to 340 340 hertz. The apparent frequency heard by the observer who is on the cliff will be 340 hertz, right? So the apparent frequency heard by the person on the cliff is 340 hertz, right? Okay, that's done. So the first question is done. And then they are saying an echo of the horn is produced by the cliff. Find the frequency of the echo as heard by the man in the boat, right? So an echo of the horn, right? Echoes are produced when the sound waves reflects back to the same person who produced the sound, right? So the person who produced the sound is on the boat itself, right? So the observer is on the person who produced the sound, I mean like the horn, is inside the boat, right? So this sound is going to collide with this cliff, right? It's going to collide with this cliff and it's going to return back, right? It's going to return back to the same person, right? So now, while it is returning back, while the sound source is returning back, the observer is, like in this case, now the observer is the boat. Now the observer is the boat. Observer is moving forward, sound source is coming towards it. So in that case, what is this? This is once again a relative motion between the sound and the observer, source and the observer. So for this case, of course, we need to consider the cliff as the source, right? So the sound that was initially produced, it's going to go and it's going to collide. It's going to reflect back with what frequency? F dash. So we need to consider the cliff as the source in this case, right? So let us assume the cliff as the source, right? Cliff. So this is the source now. So it's going to produce a sound frequency F dash of what? 340 hertz. Now the person on the boat, right? So let us assume he's somewhere here, right? So this is the observer. So if this is the observer, observer is moving forward with 5 meters per second velocity, right? So yes, what is the speed of sound? 340, right? So what will be the apparent frequency heard by the observer on the boat? We can assume it to be as F double dash, right? So we can write an equation for F double dash, once again using what? The relative velocity of sound. So actually it should be the velocity of sound relative to the observer. All right. So velocity of sound relative to the observer, right? So if we use it, velocity of sound relative to observer, and then velocity of sound once again relative to source, right? So the observer in this case is moving forward, right? The observer is moving forward, sound is moving towards him. So both the parties are moving towards each other. So the relative velocity is taken how? By the addition between them. 5 plus 340 divide by, so velocity of sound relative to source. So velocity of sound is moving forward. Source is still. Source is not moving. Source is still. So therefore, it's as it is, right? 340 itself, right? Into what is the original frequency now? Now the original frequency is not F, it is F dash. F dash is what? 340, right? It's 340. So if double dash, if you simplify, you're going to get it to be as 345 hertz. You're going to get it to be as 345 hertz, right? So the second question is also all right. Okay. So let us go for the third question. If the man hears the sound emitted by the horn and echo together, find the number of beats heard by him, right? So it's like initially the man is going to produce the sound, right? So the man is the man on the boat, right? So the man on the boat is the one who is going to produce the horn, right? So he's going to get the reflection as well. He's going to get the reflection as well. The reflection receives, I mean the echo, right? He's going to receive the echo as well, right? So the echo will reach him with what frequency? 345 hertz, right? The sound that was produced by him is 335, right? Sound that was produced by him is the in frequency 335. The sound which was echoed was 345. So the beat frequency due to both this is what? The beat frequency FB is F double dash minus F, that is 345 hertz minus 335 hertz, right? So he's going to hear 10 hertz beat frequency, right? 10 hertz beat frequency is going to be heard. All right. So this is pretty easy, right? So because so the source is initially going to produce a sound of frequency 335 that is also going to be heard by the observer of the board, and also the echo will also be heard. So when both these sound waves overlap, it's going to be heard as a beat. So how do we find the beat? By the difference between the two frequencies. The difference is 10 hertz, right? It's theory. All right. So what next? All right. So now let's go for the fourth problem. So they're saying if the boat now turns back, and so moves away from the cliff, turns back and moves away from the cliff with the same speed, what is the frequency of the echo? What is the frequency of the echo? Once again, we will have to go for a proper diagram, right? So if you go for a diagram only, it will be easy for us, right? So yes, it's like simply the boat is going to go away from the cliff, right? So this is the cliff. Let's say this is the cliff. So the boat is moving in this direction with 5 meters per second. So initially the sound is going to go in this direction with what velocity? 340 with 335 hertz initial frequency, right? So it's going to receive to the cliff f dash. We need to first of all find f dash. How do we find f dash? Relative velocity of sound relative to the observer. So initially, this is the observer. This is the observer initially, and this is the source initially, right? So observer is at rest. So therefore 340. So what is the on the denominator is relative velocity of sound relative to the source. So source is moving in the other direction, sound is moving in the other direction. Like both are moving in the opposite directions. So obviously it should be added, right? So simply we'll have to add, all right, into the original frequency. So this is what is going to be heard by an observer who is on the cliff. Actually, they're not asking this, but actually we will have to find this f dash, right? If not, we will not be able to find the echo. So okay, f dash is found. Next what? Next what happens is this is going to reflect, right? This is going to reflect. This f dash is going to reflect, and it's going to receive to the observer on the boat. In this case, the observer is on the boat. We need to consider the cliff as the source, right? So the frequency, the echo frequency heard by the observer is, let's assume f double dash. F double dash will be initially velocity of sound relative to observer. Velocity of sound relative to observer is, now the observer is still, the observer is, sorry, yeah, this is the observer, right? Now this guy is the observer, the red color. So observer is moving, sound is also moving in the same direction. So we need to subtract, right? Sounds, observer is moving in towards the left, sound is also moving towards the left. So we'll have to subtract 340 minus 5 divided by what is the denominator? Speed of sound relative to the source. Speed of sound relative to the source. So is the source in this case the cliff? The cliff is the source. The cliff is the source, right? So it's going to be 340 itself, because the cliff is not moving, right? Into f dash. F dash is what? F dash is, we have found it in the above, 340 plus 5 into 335. This is f dash, right? This is f dash. This is f dash, right? Okay, so f double dash in that case is going to be what? If you simplify it, you're going to get 325.3 hertz. 325.3 hertz. All right. So all the questions are completed, guys, right? So you will have to, I'll discuss this as well, right? So you will have to cover it properly and get back with the next paper, right? So the paper 11, you can check the paper 11 as well, right? Thank you, guys. See you on the next video.